Question number 11. We have been given two barometers. A barometer is used to measure air pressure at any place. Now, the first barometer has a thinner test tube than the second barometer, and they are both mercury barometers. Okay, now let's think about how a barometer works. The question we are asked is how much will mercury rise in the second barometer with the thicker test tube? This is a conceptual question. Let's think about how a barometer works. In a barometer, the air in the atmosphere pushes down on the mercury over here, and throughout except for the test tube. In this barometer also it will push down. The air will apply a force which is applied on the barometer like this. So as the air pushes down on the mercury, this mercury in the trough will push on the mercury over here. So the mercury in the trough will push on the mercury inside the test tube, and the force it applies is directly proportional to the cross sectional area. So the force that is applied in the thicker test tube will be greater because the cross sectional area of the thicker test tube is greater than this one. So let's call this Ft and let's call this F. Okay, after that's done, let's think about what force is applied by the mercury inside the test tube. We have some mercury over here inside the test tube. The mercury inside the test tube has mass, and therefore when we talk about F equals to mg, then we can say that the mercury inside the test tube will also apply a force downwards. So this force over here and this force over here balances out each other. The same happens over here because as the cross-sectional area increases, this force will be higher. So the force inside the thicker test tube will be higher than the force inside the thinner test tube. And again, it balances Ft over here. Because we have a higher force in here than this one, it basically means that the level should almost be the same because we have more mass of mercury over here. As we have more mass of mercury, it will take up more space, and therefore the level is same. This is a very conceptual question and you can remember this. So our correct answer is B. We need more mercury over here to counter this force, and because we need more mercury, we'll keep it at the same level and just think about increasing the thickness. Question number 12. We have been given four solids that have the same weight and they are different three-dimensional shapes put on a surface, and we have to tell which one will exert the least pressure on the surface. The first one is a sphere. Let's think about how much a sphere exerts. Okay, so let's say we are talking about this sphere over here. Now you can see that this sphere only has a very small point of contact with the surface. The point of contact will look something like this. It will almost be a dot. This is the surface area that is in contact with the surface. For the cylinder, it will look something like a line. Say for this cylinder, it will look like this. So through this line, maybe a little thicker, we have the point of contact. For a cube or a cuboid, it will look like an eraser. So we have one face in contact. For a cone, it will look like a circle, the surface area that is in contact. Maybe this circle over here. Now we know one formula, that is pressure is equal to force divided by area. This basically means that for the same force applied, the force applied by all of these shapes is the same because they have the same weight. Weight is m into g. So the force is just weight. Now, higher the area we will have, the lower the pressure we will have. That is because that's how fractions work. The higher the denominator, the smaller the fraction. Therefore, for the sphere, the area is very low and it will exert the highest pressure. The line over here, the cylinder will exert a lower pressure because area is higher. Then the square will exert a very low pressure because the area is highest. and the circle over here, the cone will also apply pressure which will be lower than the cylinder but greater than the square. Therefore C is our answer because the area over here, the surface area of square that faces down, that touches the surface, is the highest. A, highest. And because of this formula, we get that our answer is C. Question number 13. On a hot day, the pressure of the air inside a car's tire is greater than on a cold day. Why is the pressure greater? Now, let's think about what pressure actually means. If I have a container that looks like this and I have gas in it, so these are probably gas molecules quite far apart, and they're continuously moving, they are hitting the walls of the container. They are also hitting each other, but more frequently they are hitting the walls of the container. And this is what actually pressure is. The more they hit the walls, the more they bounce back, the higher the pressure. So a higher pressure basically means a higher number of collisions, so n is directly proportional to pressure and the force of each collision. So if a, a molecule applies a higher force on the wall when it collides, then it will lead to a higher pressure. Okay, let's now think about the option. Option A says the air molecules strike each other more frequently. Now, this option is completely irrelevant. The reason is we need to talk about the molecules hitting the walls, not each other. We don't care about this. We absolutely do not care about these collisions. We only care about the collisions with the walls. So, option A is irrelevant to us. Option B says the air molecules strike each other with greater force. For the same reason, we don't care about the air molecules striking each other, therefore, B is also wrong. Option C says the air molecules strike the tire walls more frequently. This seems like a a plausible option because we did talk about n being proportional to p. So, as the tire walls are struck more frequently, the pressure increases, and on a hot day the molecules will have a higher kinetic energy. They will move faster, they will move more, and therefore the number of collisions actually increases. Therefore C seems like a plausible option, so I'll star it. Option D says the number of air molecules in the tire increases. This is absolutely invalid. The number of molecules cannot increase at all. That is something we know from the conservation of mass. So D is wrong. So C seems like our correct option. Question number 14. We have a little bit of apparatus in this question. Basically, we have a microscope over here which is looking down on a beaker filled with water, and light is shown from the side. And we have pollen grains inside this beaker. Now, the first thing that comes to my mind is how will the pollen grains look? What is the reason for shining this light? So, you can actually demonstrate this using, basically try to shine a light in front of smoke. When you shine light on smoke, you will see that the smoke particles literally start glowing. They will reflect the light, and because they are so small, they will look like very small specks of actual light. They are just smoke particles which are reflecting light. The same will happen to pollen grains over here. The pollen grains will look like specks of light. Seeing is written in the question. We see specks of light, and I am telling you that those are the pollen grains. They cannot be water molecules because water molecules do not reflect light. Light can refract through water. Water molecules do not reflect light. Okay, let's move to the question. We have been asked what are the moving specks of light? Okay, option A says pollen grains being hit by other pollen grains. Now, this is a plausible option because it says that the specks of light are pollen grains, but it also says that they are being hit by other pollen grains, which is a very rare occurrence. The reason is maybe we have some 1000 pollen grains inside this beaker of water, but we literally have millions of water molecules. And the pollen grains are so small, they will be very far apart. So they won't be hitting each other so often that they cause a very jerky motion. So option A is a rare occurrence, though we are not sure. This might be our answer. Option B says pollen grains being hit by other water molecules. This seems like a very good option because, yes, there are pollen grains which are the specks of light and they are continuously getting hit by fast moving water molecules. And that is why they have a jerky motion, which is also called as Brownian motion. They will have motion like this, they will move in a path like this because they are continuously getting hit by water molecules. This seems like the correct option. Let's think about option C, water molecules being hit by other water molecules. This is absolutely wrong because the specks of light are not water molecules. Water molecules do not shine light back. You cannot see water molecules in light. So this is wrong. Option D says water molecules being hit by pollen grains. This is an even wrong option because the same reason water molecules do not shine back light and they cannot be hit by pollen grains so often that they cause a very jerky motion. So this is also wrong. Our correct option is option B. Question 15. When a thermometer is calibrated, the fixed points are marked. What are fixed points? Okay, for this question, you need to know what fixed points are. So, the best explanation, the best example for fixed points is the boiling point of water and the freezing point of water. So, we all know that the boiling point of water is at 100 degrees Celsius. That's when water gets converted to steam. And the freezing point, where the water gets converted to ice, is at 0 degrees Celsius. The reason why they are fixed points is that on the Celsius scale, these will always remain constant if you are at sea level. If you are on Earth and you are at sea level, the boiling point of water, pure water, will always be 100 degrees. So when you are calibrating a thermometer, you can easily use this universal value. You can boil some water, put the thermometer inside that boiling water, and check till where the mercury or whatever liquid rises. Once you know that that is 100 degrees Celsius, you can calibrate it like that. And you can do the same for 0, and then you can divide it 100 markings in between of that. And that is how fixed points work. So let's check through the options. What are fixed points? All the marks on the temperature scale which cannot be removed. No, all the marks are not fixed points. They are the ones which can be easily reproduced. So option A is wrong. B, all the marks of the temperature scale. Again, this is wrong. C, the lowest and highest temperature shown on the thermometer. Now this will vary for every thermometer. Some thermometer might have from 10 degrees to 100 degrees. A same brand thermometer might have from 10 to 99 degrees. So this is also wrong because this varies. Option D, this should be the correct option. Two temperatures of known values which are easily reproduced. Absolutely. Like as I gave you the example, two temperatures of known value which can be easily reproduced. Water is available everywhere. You are almost at sea level everywhere. You can get pure water. So just use it and you will get to 100 degrees Celsius very easily, and also 0 degrees Celsius. So option D is correct. Option D is the correct one. Question number 16. Which statement defines the thermal capacity or heat capacity of a solid body? Okay, thermal capacity or heat capacity? I rather like the word heat capacity because it relates to specific heat capacity. So, what is thermal capacity? Basically, if you have 1 gram of H2O, so if you have water at maybe 20 degrees Celsius, and 1 gram of it, that is equal to 1 milliliter, but we don't care about that. Now, if you provided heat, 4.2 joules heat, if you provide 4.2 joules heat to water, you will raise it to 21 degrees Celsius and it will remain 1 gram of H2O because mass cannot be destroyed. This value over here is the heat capacity. So it is basically how much energy you need to raise the temperature of 1 gram of a substance by 1 degree Celsius. So delta T was equal to 1 degree Celsius because we went from 20 degrees to 21 degrees, and we did it for 1 gram of H2O. So if we wanted it for 2 grams, if we wanted for 2 grams to raise from 20 degrees to 21 degrees Celsius, we would have needed 4.2 into 2, which is 8.4 joules. This is what thermal capacity or heat capacity is. The energy needed to raise the temperature by a certain amount of a unit degree. Okay, so let's check the options now. Option A, we have energy needed to melt the body without a change in temperature. No, that's the latent heat capacity. So this is wrong. Option B says the energy needed to raise the temperature of the body by 1 degree Celsius. Now this is absolutely correct. This is what I have been explaining over here. So option B is correct. Let's see the other options though. The increase in volume of a body when its temperature is raised by 1 degree Celsius. We don't care about the volume when we talk about heat capacity, so this is wrong. The total amount of internal energy in the body. We don't care about the total amount of internal energy, so this is also wrong. We just care about the change in energy. So B is our answer. Question number 17. A substance can exist in 3 different states: solid, liquid, or gas. We have been given 2 statements, 2 changes. The first change is molecules come closer but continue to travel throughout the substance. So I'll write it like this. Molecules come closer. So intermolecular space reduces, but they still continue to travel. Okay, so their motion is continuous. Still, they were moving before and they're still moving. And second, molecules stop traveling throughout the substance and just vibrate about fixed positions. So stop motion but vibrate. So over here we can immediately see from this information that the intermolecular space is decreased. That means we are either going from liquids to solids or gases to liquids, because those are the only 2 changes in which the intermolecular space is decreased. Now eliminating the other options, now we can see continue to travel. When a substance goes from liquids to solid, the molecules don't continue to travel, they stop. That means that our correct answer over here is liquid to gas, because molecules will still move and the intermolecular space will become less. I'm sorry, gas to liquid, because the intermolecular space decreases like this. Now for this change, molecules stop motion but vibrate. Okay, so we can immediately see that this is coming to solids, because only in solids molecules only vibrate and stop motion. So we know that on the other end we have solid. On this end we may have liquids, we may have gas. Now we can check the options. Okay, option A says, okay, so change 1 must be condensation, because we know for sure that it is gas to liquid. So option A and option B are the only ones that can be true. C and D are eliminated. Now change 2 is either melting or solidification. We are going from liquid to solid or gas to solid. So one is called solidification, other is called sublimation, and we have the option for solidification available. So B is correct. B says condensation for this and solidification for this. So B is our answer. Question number 18. We have 2 surfaces. One over here, this surface on the top is cold, the bottom one is hot, and we have a gap in between. In between, the gap can contain air, solid iron, vacuum, or liquid water. Let's read the question. Which row shows whether heat can be transferred between the surface by conduction and convection? Okay, so we'll check through the options. Option A says air. and conduction yes and convection no. This is inaccurate because air can only transfer heat through convection and it cannot transfer through conduction. So this option is absolutely wrong. Option B says iron, which is a solid, conduction yes and convection no. This seems like a promising option because conduction can happen through iron because it is a solid, and convection cannot because it is a solid. Convection only happens in gases and liquids. So this seems like a promising option. Option C says vacuum, conduction no, convection yes. Neither conduction nor convection can happen through vacuum. The only thing that can happen is radiation. Therefore, this option is wrong. Option D says water, conduction yes, convection no. Okay. There is just a little amount of conduction through water, but I don't think IGCSE will test you on that. For convection, the option is no for water, which is absolutely wrong. We know that convection can happen through water. Therefore, this option is wrong because it says convection is no. So the only correct option, the only valid option over here is option B. Question 19. We have been given a test tube that looks like this, which is filled with water to almost the brim. Now we have a wire case over here, which is basically something made of metal, which is stopping this ice block over here to go upwards because ice rises. It is stopping ice from going upwards. Now we are providing heat at this point over here in this region to the test tube. We have been told that the water boils before the ice melts. So basically, when we provide heat, this water will start boiling before the ice even melts. And we have been asked to tell the reason why this happens. Okay, so one of the reason that comes right off my mind is that it takes time for heat to transfer from here to here. We are heating over here, so this part of water's portion will be heated, but it will take a lot of time for heat to go from here to here, and that is because water does not conduct heat very well. Water is a very bad conductor of heat. Let's check through the options now. Option A says convection currents are circulating throughout the water. Well, that is true. But convection currents, first of all, are slow. Secondly, they are already at the top, so they won't move so much. Convection currents try to go towards the top. Hot water rises, so it will not flow so much. And thirdly, if that was the case, if A was the option that was correct, then ice would have melted. Option A literally is saying that heat is reaching ice in time. And we want to talk about the opposite situation. We want to talk about that heat does not reach ice. Therefore, option A is completely wrong. Option B says ice is a poor emitter of thermal energy. Now, we do not care about ice being a poor emitter. We care about ice being an absorber. And the reason is because right now ice is absorbing heat, not giving it away. So B is just invalid. It's irrelevant. Option C says water is a poor conductor of thermal energy. We discussed this at the beginning. The main reason why heat is not reaching from here to ice, from the top to the ice to the bottom, is because water doesn't conduct heat very well. So C is correct. Let's also discuss option D. Option D says wire gauze is a good conductor of thermal energy. That is correct. But well, if the heat won't even reach this point, if the heat won't even reach from the top to the bottom, then the point of wire gauze being a good conductor is irrelevant to us. So this is also wrong. We don't even care about wire gauze being a good conductor or not. So C is our correct option. Question number 20. So we have been given some water which has waves in it. So basically these are the wave fronts of water. This whole area over there's this is a container, there's water in it, and the water has waves in it. So these are the wave fronts. over here, and we have a barrier which has a gap over here. This is the gap which is almost equal to the wavelength of water. And we have been asked what will happen after this barrier. So how will the wavefront look? So we can immediately see that this is a question related to diffraction. And what is diffraction? Well, diffraction is basically the bending of waves. So when waves bend like this, when they pass through a barrier. And thirdly, well, water over here has almost the same amount of wavelength as this barrier, and according to diffraction, that means that water waves will bend a lot. Therefore, water will look something like this after being diffracted towards the right of the barrier. Okay, let's check the options now. Option A says that water will continue to go in a straight path and will not diffract. So option A is wrong. It will definitely diffract. Option B, option B says the same thing, but the waves are a little more spread, which is also again wrong. Option C, in option C, water is diffracted, but the point is okay. So option C looks something like this. These are the wave fronts. Option C just says this, which is absolutely wrong. If we have wave fronts that are like this, water will rather go something like this. It will cover the complete area. Therefore, option C is wrong because water diffracts in this path. It will look like this. It will spread, not just have small wave fronts like this. Okay, so option C is wrong, then D should be our answer. And yes, D is because D showcases this phenomena as I explained over here. So D is correct.